Welcome to Acme Software Works, where the craft of software engineering is practiced. In this video we will be exploring the quicksort algorithm. The quicksort is a recursive algorithm and is commonly referred to as an algorithm which uses a divide and conquer method.
The quicksort algorithm starts by designating a pivot, which may be any element. In the case we will be examining, the last element of the array will be designated as the first pivot. It then takes a portion of the array, known as a partition, and after that the last element of the partition will be the pivot. Moves elements smaller than the pivot to the left, elements greater or equal to the right in the partition, then places the pivot between the smaller and larger elements, which is its sorted location. The quicksort algorithm uses recursive calls to the quicksort function. With each call a new partition is defined with a new pivot which is the last element. The quicksort function contains two recursive calls, one with a partition to the left of the previous pivot and one to the right. The quicksort function terminates when the partition it receives is one element or less. The partition is defined by the low and high arguments to the quicksort function. The quicksort algorithm which is implemented here consists of two functions. The first is the primary function and has two recursive calls. The second is called from the primary and is the workhorse which deals with the partitions and does the sorting. The partition function derives the pivot from the last element, then in a loop, searches starting at the first element of the partition, for elements that are less than the pivot. When it finds an element that is less, it increments the smaller index and swaps the element at the smaller index with the element at the search index. When a smaller element is encountered and the smaller index is increased, this ensures that all elements to the left are smaller than the pivot. Note that the smaller index is only increased when the search index encounters an element smaller than the pivot. This in effect moves the smaller elements to the left in the partition and the larger ones to the right, and finally the pivot is swapped to the location of the smaller index +1, which is between the smaller and the larger elements and its final sorted location. Then it returns the pivot index to the primary function, quicksort, which will then be used to create the next partition. Note that the quicksort function has two recursive calls, one with a partition before the previous pivot and one with it after. Because the arguments to the calls to the quicksort function are based on the location of the previous pivot, the partitions will become increasingly smaller. When the size of the partition is 2, which is the smallest partition, the partition function will end with a sorted partition. So when all the partitions reduce 2 or smaller, the entire array is sorted. Now let's watch as this unfolds. When the quicksort function is first called, the low argument is set to 0 and high argument is set to 24. There are 25 elements in the array, making the first partition the entire array. Using the last element as the pivot, makes 85 the first pivot. The search starts at the first element of the partition, then compares the search element with the pivot. In this case 98 is not smaller, so it moves on to the next element, which is smaller, so it increments the smaller index, which will now point at the 98, and swaps it with the 35, and then again the 47 is smaller than the pivot, so once again it will swap it with the element at search index. Note that the 98 will continue to move to the right as long as the elements at the search index are smaller than the pivot. You will notice that all the elements left of and including the smaller index, after the swap, are and will remain smaller than the pivot.
Note the smaller elements are cyan, the current search is white and the current pivot is yellow. The partition is within the square braces and elements that have not been checked against the pivot or are larger than the pivot are blue.
The two functions variables are displayed here.
The one function which was not been included in the simulation is the swap function, so here is a quick look to make it clear how it functions. It is handed pointers to the elements that are to be swapped. It stores the element pointed to by the first argument, xp, in a temporary variable, then places the element pointed to by the second argument, yp, in the place where the first argument is pointing. Then finally the temporary value is placed where the second argument, yp, is pointing. And now the pivot, 85, is swapped with element 1 beyond the smaller index, which is also larger than the pivot, making all elements smaller than the pivot 85, to left, and all element larger to the right. Now the partition is 0 to 19 and is left of 85, the previous pivot, and its pivot, the last element of the partition, is 16. Note that the first few elements of the partition were larger than the pivot, so the smaller index did not move until it encountered the 6, and will not move again until the 7, leaving somewhat of a gap between the smaller index and the search index. Note the recursive call stack. Each time a recursive call is made, it will be displayed here. And the previous pivot will be displayed here with an arrow showing which internal call was made, either the pivot to left or the right.
Note the maximum depth that has been reached is indicated here.
The quicksort's average big O is n log n, and its best case is n squared.
When a recursive calls low and high arguments indicate a partition of 1 or less, the arguments shown on the recursive stack will be red. When this occurs, the recursive call to the quicksort function will terminate.
Note the partition to the right of the 16, which have been created by the second recursive call, extends to the 85, an element which is in its sorted location, and all the elements in between are not. This will always be the case. Partitions never contain previous pivots, which results in the partition becoming smaller and smaller.
When recursive calls are made from the function call, with the partition to the left, note that even if it terminates due to the partition being too small, the second recursive call, with the partition to the right, will be executed. This means that both internal recursive calls must terminate by receiving a partition too small, before the program can traverse back up the recursive stack, and finally terminate. Now let's speed it up and watch is finish.
You will notice that on occasion, the from and to of the swap are the same location. It is more efficient to let this occur than test for it before each swap. Thank you for watching. Please like and subscribe.